and gentlemen, welcome to the show. My name is Gert Nielsen. I work for contractor in Norway, GK Kulde. I've been a consultant for 16 years, so it's good to come out in the real world. I will tell you something about borehole installations or water to heat pumps, what to use and where to use it. Why we examine this, that is, in Norway there's a consensus that the most economical heat pump solution is borehole based. That is backed by, I believe, or what I call mushroom theory. Mushroom theory, that means it lives in the dark and it feeds on horse shit. Widespread consensus based on, I believe, should arise suspicion. Now, where are we examining? We are located up here, there, Norway, and we check out Bergen, Karasjok, Oslo, Røros, and Tromsø. The distance is almost 1,800 kilometers long. It's a long country. As the crow flies, it's actually from Belgrade to Oslo. So we start examining the temperature duration curves. This is what the climate in average looks like in Bergen. This is in Karasjok, and we can from this curve see that the average temperature per year is below zero. This is Oslo, this is Røros, and it's basically the same pattern as Oslo because it's inland. And then there's Tromsø, which is basically the same pattern as Bergen because both of them are on the west coast. See the average temperature design outdoor in Bergen is -12, in Karasjok it's -40, in Røros -30, in Tromsø -15, almost the same as in Bergen. But the average temperature in Tromsø is about 3.4, in Karasjok -1.5, and Bergen is in average the warmest place in Norway, 8.2 degrees. The sad thing is we got average all year. So midsummer temperatures 8.2, Christmas temperatures 8.2. So this is I've taken this building and moved it around the country. This is what the situation would look like in Bergen. No, in Oslo, sorry. We have a heat demand there of radiator heat demand of 538 kilowatts. We've got 400 kilowatts of heat loss here. We've got 138 kilowatts of heat loss in the ventilation due to this lower temperature. As Olof Fanger said it, air should be served as white wine, cold and fresh. So this gives us then, this went too fast. This is very tickly. So we see here, this is the air handling unit heat demand, depending on what the ambient design temperature is. The blue line here is the building heat demand, and this green line is what we need on the radiators to compensate for under temperature in the ventilation. So we take this is what it's designed for, but a typical situation would be like this, where we still got -28 outside, but we got 850 people working here. It's just about 20 square meters per workplace. I don't say anything about how much they actually work. I just say they are there because the heat source is. And we reduce the ventilation rate because we've usually only got about 80% presence. So we reduce the heat demand here. We reduce the heat demand here. That gives us curves like this for every one of these 5 locations. Heat demand, and here is the temperature demand in the heating systems. I won't show for all 5. But we see the annual heat energy demand in Bergen was about 800,000 kilowatt hours, and in Karasjok it was 1.8 million. It's quite higher. This is the design heat rate demand in the different cities. Now, I'm examining 3 heat pump configurations here. Don't let yourself be disturbed by this zero here. It's just referring to the evaporating temperature. This is, if the ground temperature was 0, then our evaporating temperature on a ground source heat pump system would be -10.5. if we had an outdoor temperature on a system based on a dry cooler and then going into an evaporator here, at 0 degrees outside we'd have an evaporating temperature of 9, and in a direct system we'd have an evaporating temperature of about -6. So I have these 3 configurations. I'm using 3 different compressor makes, Bitzer generic recip and screw, and a Bitzer Sabro generic SMC recip. There are 5 different localities. That gives us 45 different data sets that we have to compare. So the heat pump, the performance, what it can deliver in kilowatts, I found by just saying, okay, I go with a Sabro generic when it has a coverage of 95% on energy used on a borehole system. That is the compressor. That is what the heat pump should deliver. And we'll see some performance differences, but they mostly stem from the difference in operating ranges. Well, we could see, as in Bergen, we had a design heat demand of 675, but just a heat pump of 174 will give us 95% energy coverage. The same applies actually for Karasjok, even though it's so much colder. The relationship between the design for the heat system and the design of the heat pump is just about 25 to 30%. And you get an energy coverage of about 95%. So there's a lot of numbers here what we can see. They're very close in how effective they are. But going into the details of this, I think will go too far. But here are the different operating ranges, and that is what gives us this difference in energy coverage. The blue line here is the generic recip of Bitzer. This is the Bitzer generic screw, the red one, and the green one is the SMC operating range. Now, the isentropic and volumetric efficiencies of this is assessed by the polynomials that we can get out from Bitzer's calculation program. From Sabro, I got it from a guy, Uffe Christiansen. Hey, I can say it now because he won't get into trouble, because if he's into trouble here, he's been in for a long time because he's dead. There's very little hope of him getting any better. And then we had to correct the isentropic efficiency at off design. So I've been using again the source codes from Sabro, and on the curve fitting on the screws I've used efficiency curves from Sabro and Georg Rassel, because I said, well, the physics in the screw compressors are very much the same. So if I use the one program or the other program, at least I'll be honest about it. So people can say, well, that's not correct. Probably it isn't, but it's correct enough. So we can see here, the dotted lines are the ones I've been using in my calculation program, and they're pretty close to what I actually got out of the calculation programs from the different producers. The motor efficiency is found from an IE3 class 2-pole 50 Hz motor. Off-design efficiency is compensated, and I use actually the calculation efficiency as an IE1 motor because I have a VSD drive, and the VSD will introduce some losses. So this is very tickly. This is the different efficiency lines for the different motors, and this is the one. This is the VSD efficiency. So the one I've been using is actually the worst one. So energy demand for the heat extraction, we have to take this into account, and usually HVAC engineers don't. But we have to take it into account. And I landed on a number that says about 150 watts per well times 8,760 hours, because Usually these pumps run all the time. The demand for intermediate dry cooler installations, I came to a number of 150 watts per kilowatt heat extracted times the actual runtime. And the fan power I found from Gintner's program from 2015. So we can see this is it's quite nice straight line on this. So these are the COPs we were looking at. This is COP from heat pump, the COP from including extract, and then the total system. And that means we have to add the auxiliary heat needed, the last 5% or whatever it turns out to be. So we'll see here, the blue ones in the back is the COPs for the annual COPs for systems without the heat extraction. Then the red, I include the heat extraction, and then the green, I include the auxiliary heat. I haven't included the distribution pumping because that will be the same for all four. So it's the difference that doesn't make a difference. Therefore, it's just clouding up the picture. But we can see on this, we might see it here that these are borehole installations. The three here, the borehole, the dry cooler, and then the air evaporator. It's from Bergen, Karasjok, and Oslo. I didn't find room enough on this one for all of them. Here they are, all of them. This is borehole, dry cooler, air evaporator, and we can see the relative energy savings. In the Bergen area, borehole will give you an average energy saving of about 72%. And the direct evaporating will give you just about 68% in energy savings. But we can see a very big difference on the system configuration on energy efficiency in Karasjok. And that should not be shocking. But the thing is, I was very surprised that the difference in the Oslo area, because the Oslo area is beginning to look like a Swiss cheese, because they're boring so many holes that they got problems when they want to put in a new line or tunnel for roads, because they will hit people's energy bills. So I was surprised that the savings was just about 10 percentage points, because now it's investment we're talking about here, and this is actually, these numbers are what triggered me to examine this in the first place, because we can see this 12,500 euros per well. That is what Statsbygg, the Norwegian state government agency for building, uses when they budget. When they make up budgets for new projects, they use that number for assessing what an energy well will cost. So we are at the range of 1,500 to 1,600 euros per kilowatt just in the heat extraction system. So the heat pump is an afterthought. I used, as a heat pump unit, I used standard unit equipment estimated from other projects, price list. I got help from suppliers to get the budget prices. And Alex actually helped me with this one, where we estimated the evaporator cost in a packet unit to be about 15% of the total cost. So I've air heated evaporator cost. I've used Gintner's calculation software, and it's there from there. The dry cooler investment is about estimated to 75% of the air heated evaporator. I guess that's too high. And the pipe work from dry cooler is estimated to about 350,000 euros. Now, I can see some of you are wrinkling, but remember, Norway is a high-cost country, okay? And the pump investment, they are basically based on price lists and experience. So I got these curves to work with, and the evaporator investment and the pump investments are set up like this. And this gives me this picture. You see, this is basically the investment, the heat pump investment is very much the same, and then we have the boreholes. See how much it adds in the total investment. And this is the annual cost. I used an energy cost of about €1 per kilowatt hours. It's very close to what Jan used. So, and we can see the annual cost of this is actually cheapest. The cheapest solution is to run with a direct evaporator in the air and not using the boreholes. And the thing is, I think the boreholes are a brilliant solution if you want no hassle. You want to have a stable heat source into your heat pump, but you should not believe that this is the most economical solution. It's the most energy efficient solution, and that's not the same thing. So we look at the simple payback here. You see the simple payback in the Bergen area for borehole installation would be somewhere around 7 to 6 years, 6 to 7 years. But we saw the difference in energy savings were not that big. In the Bergen area it was about 4%, in Karasjok area it was quite a bit more, but in the Oslo area it was just 10% point. So these 10 percentage points has to pay for this. So if we just look at the simple payback for the boreholes alone, we can see in the Bergen area, if you compare it to a direct evaporator placed in the outside air, the payback would be just about 60 years. Most people will be dead by then. Most of them, you know, to do today would be dead when you paid it back. Even in Karasjok, where it's so cold, we have a payback time of about 15. In the Oslo area, where they use it like mad, it's between 15 and 30 years of payback. So, the borehole installation will provide a stable heat source, and that might be very important, but only if you're able to recharge the installation during the cooling season. We have some very many installations in Norway where they use it to household heating. They just drill the hole, fill out, extract the heat. 3 or 4 years later, the well freezes up. Nice. In cold areas, like in Karasjok, you won't have any cooling demand in summer because the temperature does not go so high that you actually develop a cooling demand. So you must find some other way of recharging it. So the borehole installation is not the most economical solution. It's the most energy efficient solution, but it's not the most economical efficient solution. The most of it seems to be this, but where the air is directly on the evaporator. This solution, however, will probably mean a very big charge, and the heat pump can usually not be applied as a part of the cooling installations. But if you come to this presentation, the internal reversible ammonia chiller, I can give you some hints about what you can do. Then the commercial's done. Thank you for staying awake.